Hello and welcome to another lecture session of Introduction to Astrophysical Fluids. Previously, after deriving magnetohydrodynamic equations, that is the monofluid model of plasma from kinetic theory and multifluid models of plasma, we discussed various interesting features of magnetohydrodynamic fluids, right? So first we discussed the importance of Lorentz force. How can we decompose the Lorentz force into two type of contributions? One is like a magnetic pressure, another is a tension term. Okay, then also we defined plasma beta, and it was followed by a discussion on the Frozen-in theorem for a magnetohydrodynamic fluid. Okay, so and then we also saw different types of implicit invariance. So we started by mass conservation, then we talked about the very subtle case of linear momentum conservation, then we talked about some scalar invariants, of which a real scalar invariant was the total energy, which had three parts: kinetic energy, magnetic energy, and compressible thermodynamic energy or compressible potential energy. And then we also introduced several pseudo-scalars, okay, which we called the helicities. Okay, so one was maybe the kinetic helicity is purely, of course, you may be known that. This is a purely hydrodynamic concept. You may be accustomed with this concept already. Then another was like the cross helicity, that is the dot. So kinetic helicity is nothing but the dot product of kinetic helicity density. Okay, whatever we will talk about in terms of densities. Okay, when you integrate that density in the whole space, then you get the total helicity. Okay, so kinetic helicity was nothing but the scalar product of velocity and the vorticity vector. Okay, then cross helicity was introduced. It was the scalar product of velocity and the magnetic field vector. And finally we said that there is another helicity which is of very importance in MHD, okay, in magnetohydrodynamic case, mostly in turbulence and in other type of phenomena. Okay, so that was the magnetic helicity, which is the scalar product of magnetic field and magnetic vector potential E. Okay, so in this and after so in this part we also said a few words, okay, if you can remember, that under which circumstances in a practical case we can really assume that our system can follow ideal MHD equations. Okay, and finally we talked about the very interesting LSSR variables and how can the equations of incompressible MHD can equivalently be projected in the form, in terms of the LSSR variables. One thing was very easy to understand, very direct, but I did not really mention when I just followed the lectures. I just thought that it is maybe good to say you directly. That is, in incompressible MHD, as V and B both are divergence-less vectors, V plus B and V minus B, that means Z plus and Z minus, they are also divergence-less. Okay, so the two LSSR variables are actually two solenoidal vectors. So the whole set of MHD equations in terms of LSSR variables are constituted by divergence of Z plus is equal to 0, divergence of Z minus is equal to 0, and two evolution equations, one for Z plus and one for Z minus. That constitutes the complete dynamical theory. In today's discussion, we will start discussing the response of an MHD fluid towards an external very weak or first order perturbation, linear perturbation. And actually we will see that there will be interesting wave modes. Okay, and of course that says that our chosen initial system, which is of course a steady system, is such a steady system that that it corresponds actually a stable equilibrium. Is something analogous to stable equilibrium system. Okay, and that's why the system, when it is perturbed a bit, it responds in terms of the linear modes. Okay, whenever we are discussing in this part the waves in MHD fluid, we will follow exactly the same steps as what we did for the neutral fluids. So if you remember that, first of all we start with a steady initial state, okay, and then we perturb every quantity, okay, by a very weak, small amount, okay, and what we call weak perturbations or linear perturbations, and sometimes we call first order perturbations, okay. And then we study the nature of the response given by the MHD fluid, and how, first of all, after just expressing every quantity as its initial value plus the first order perturbation, we try to replace all the values in the original equations, and finally we just drop out all the zeroth order terms, which are basically nullifying each other due to the zeroth order equations, and then we also neglect the second order, neglect the terms which are of second order smallness, and then we have a set of linear equations. Okay, so with that linear equation, finally we assume plane wave type of solution, okay, and then we try to we derive some relation between like omega, the frequency, and the wave vector k, which we call in general the dispersion relation. Okay, now let's do that formally over here. So here, first of all, when we study the response of an MHD fluid towards a weak perturbation, okay, we will, for the sake of simplicity, at the first step neglect forcing and viscosity. It is always a very good question that what happens to the wave modes or to the nature of response if we take the forcing or the viscosity into account. That's you to think. Okay, it's a very good question actually. Now we start from an initial state which is a static steady state. So not only that it's a steady, that means every quantity is independent of time, but the velocity in the initial state is 0. So we start with a static case. Okay, and then we perturb the system by a little bit. So rho becomes rho 0 plus rho 1, where the initial hydrostatic density was rho 0. V becomes V1 only because V0 is 0 by definition. Okay, so B is the magnetic field, and it is just the initial B0 plus the fluctuation. Okay, plus the perturbation. And same thing for the pressure. So initial pressure plus, so which is P0 plus P1, first order perturbation. Now when we linearize the continuity equation, then this equation becomes del rho 1 del T. Okay, because if you remember how to write that, so it should write del rho 0 plus rho 1 del T plus divergence of rho 0 plus rho 1 times V is only V1, so it would be equal to 0. Now you see del rho 0 del T, okay, del rho 0 del T and divergence of rho 0, so it's already 0 because rho 0 V0 is 0, V0 is 0, so that's why the zeroth order term is 0. So we only have del rho 1 del T plus divergence of rho 0 V1. We also neglect rho 1 V1 because of the second order smallness. Okay, so finally we have del rho 1 del T, so which is, so always just cross check that whether your term is of first order smallness or not. So del rho 1 del T is of course with first order smallness plus rho 0 divergence of V1 is equal to 0. So that is also of first order smallness. Okay, so this is the linearized equation of continuity. Then we do the same thing for the momentum evolution equation, where you can easily understand that this is again, so the rho 0, so there will be rho times del V del T. Now I mean only rho 0 can be taken because there is no V0. So I mean in order that the total thing to be of first order, rho 0 should be, I mean the part of rho should contribute to 0th order, because the only non-zero contribution from this part would come in the first order. There is no 0th order for this part. Okay. So that's why this part is rho 0 del V1 del T, and you know that there should be no contribution from the part V1 nabla V1 because of its second order smallness. So we forget that. So that is equal to then minus gradient of P1. Okay. So gradient of P0 will be, I mean, balancing with the 0th order term of the Lorentz force, of course, over here. And you see that here we can actually, if you remember, we can actually neglect the body force, or the, for example, some force like gravity, only because you have here another term other than the P. Okay, so that is the Lorentz force. If B wala term, okay, this term, this Lorentz force term is not present there, then we have to take into account the body force, and that is our very usual I mean hydrostatic equilibrium and the hydrostatic first order perturbation, okay, under gravity or under some conservative force field. But here we really don't need that. That is simply because that we have this term and this term. Okay, so in the, I mean, even in the 0th order, so for example in the 0th order what happens, just you can take a look, minus plus 1 by mu 0. So so this one will be curl of B0 and B0, and of course B0, if you just choose this to be constant, then this is 0, but if you don't choose this to be constant, then this is simply, I mean you don't need to consider this to be a constant in space, but it will then simply be cancelled by gradient of P0. Okay, so now only surviving term is this one, 1 by mu 0 curl of B1 cross B0. Why? Because if both are 0, that will be 0th order term and will be taken care by the 0th order contribution of pressure. Okay, then if here you have curl of B0 and here you have B1, okay, so that is also a bit typical, because most of the cases we have seen that the magnetic field, the initial magnetic fields are in general uniform in space. Maybe sometimes they can have some time dependence, but curl of B0 is almost uniform in space. But there can be actually instances where you can actually write 1 by mu 0. So what I just said 2 minutes ago, actually there is no inhibition in writing this one, that you can totally write, but here just for the sake of simplicity we have not written this. Okay, so this is somehow a simplified form, and we cannot write both as B1 because that would get a second order smallness, so we forget that. So finally we can write del V1 del T is equal to minus gradient of P1 by rho 0 plus curl of B1 small b1 cross small b0. How did we get that? We have simply got that just by replacing this b by, this small capital B by this small b, and that was quite easy, because if you simply see that if you divide everything by rho 0, then you have this term, and here you have mu 0 rho 0, so then you divide into b1 and b0, one mu 0 rho 0 over here and another mu 0 rho 0 over there. Okay, you are done. Now the third equation of magnetohydrodynamics is the equation of Faraday. So equation of induction, okay, which simply says that del B1 del T is equal to curl of V cross B. Now once again, V cannot have any V0 amount. So in order that the total thing should be exactly of first order, zeroth order cannot be there because zeroth order will be cancelled by the zeroth order part of in the left side, okay, left hand side. So the first order term will simply be this one, the only possibility, because V0 is 0. So there cannot be any term like curl of V0 cross small b1. Okay, here I can write, so the original equation is in terms of capital B, but just by dividing every size by root over mu 0 rho 0, you can just write this thing simply. Okay, so and you can define your small b just by like this. Okay, so then your Faraday equation is del small b1 del T is equal to curl of V1 cross small b0. Okay, and finally we consider a polytropic MHD fluid. So polytropic fluid means P is equal to K rho to the gamma, but when we are talking in terms of the first order perturbations, if you recall what we did for normal, ordinary hydrodynamic fluid, we said that even if the equation is a polytropic, there will be always a proportionality relation, okay, where between the first order perturbation in pressure and first order perturbation in density, and the proportionality constant is nothing but the equilibrium sound speed squared. So gamma p rho by rho 0. Okay, so we are done. We have 4 equations which we need. Okay, so now what we do as a next step, we simply assume plane wave solutions for the perturbed quantities. So for an arbitrary perturbed quantity psi, we can write the perturbed quantity as psi 1, which will be equal to psi 1 0, that is the amplitude, times e to the power I k dot r minus omega t. Okay, so you can also like reason this in this part, that as these equations are linear in nature for all b1 v1 p1 rho 1, so for all these quantities simply we can assume the solution for every perturbed quantity as a sum of the Fourier components, and then we just choose one single Fourier component and we will study the relation between the frequency and the wave vector for that particular Fourier component. So that is the philosophy of this treatment. Okay, so then finally you can just substitute all this type of plane wave solutions in the previous equations. That means this one, this one, this one, and this one, and finally you will be given this thing. So omega p1 is equal to rho 0 cs square k dot v1. Now this one is not exactly obtained from the continuity equation. This one can be obtained if you simply write the continuity. What can you obtain from the continuity equation? So if you just assume this type of solution, this one, then any del del t will be simply converted into minus I omega, and any nabla will be converted with Ik, right? So this thing will be minus I omega rho 1 cap. So that is the simply the Fourier transform of this. So if you want, or you can just write like this, that is okay. Maybe in case it is confusing, I can just write like this: rho 1 0 plus rho 0 k, so there should be k, so there will be an Ik dot v1, that is equal to 0. Now you just multiply cs square throughout. So cs square rho 1 0 will give you p1 0. Okay, and here you will have I rho 0 cs square k dot v1. That's where we use this relation. And then you just take I out of the equation. So your omega P1 will simply be equal to rho 0 C square K dot V1. Okay. So, once again, so this is very easy to understand. You just have to multiply C square, to the both sides of the linearized continuity equation. And what is this? This is the, so this is the linearized momentum evolution equation, which gives you simply omega V1 is equal to K times P1 by rho 0 plus B0 dot B1 minus B0 K parallel B1. Now what is K parallel? K parallel is nothing but the projection of the propagation vector, okay, in the direction of B0. Okay, so that's another way of writing. So if you want, this is nothing but B0 dot K. Okay, and this is the induction equation, as one can easily guess, and that will be equal to omega B1 small b1 is equal to minus small b0 K parallel V1 plus small b0 times K dot V1. Okay, so once again this is nothing but B0 dot K. So there will be B0 dot K V1 minus plus B0 times K dot V1. Okay, so you already can see that this gives us the complete set of equations which are no longer differential equations, but they are a set of algebraic equations. Now we have three algebraic equations and we have actually three unknowns. Which are those three unknowns? One is V1, one is B1, one is P1, and our basic objective is to get rid of all these three to get the relation between omega and K, which is known as the dispersion relation. And if that dispersion relation can give us real frequency, then we will confirm that there will be linear wave modes. If there will be an imaginary part in the omega, then we have the possibility of a linear instability. Okay, so if we just eliminating at the first step B1 and P1, we simply get omega square minus K dot B0 times V1 is equal to CS square plus B0 square times K dot V1 minus V1 dot B0 K dot B0. Everything up to this total thing is multiplied with K vector minus K dot B0 times K dot V1 times B0. Okay, so this is the whole thing where you cannot see P1, you cannot see B1, the only variable is V1. Now, so this is another technique when you have not one equation but you have an equation like this. So from that you can also just so directly you cannot find from here, so just from here directly you cannot find omega as a function of K. So first of all you have to get rid of two unknowns and then you just reduce everything in only one vectorial unknown, and here which is the V1, and then what you have to do, this is a classical trick that you have to learn. So now if first of all we would do some smart choice of the direction of the propagation vector, and that choice for our case will be, and you will see why this is very good, because if we just choose without losing any generality that our K is having two components, so along X direction there is no component for K, only K perpendicular is along Y direction and K parallel is about Z direction. That is why I am saying once again this is K parallel, because the parallel sign comes when it is parallel to capital B0 or small b0. Okay, so whatever, that is not a problem because both have the same direction here. Now capital B0 Okay, so this one simply will be written as B0 times Ez cap, and then you can simply say that the y direction will be perpendicular to B0, so that's why this is K parallel perpendicular, and Z direction is parallel to B0, that's why there is K parallel. Okay, if we project those equations, I mean in this choice of K and B0, then the total equation, this one, as you can easily understand, this one is a vector equation in V1, so there should be 3 component equations, and we can write the whole set of 3 component scalar equations corresponding to every component in matrix form. And this matrix is now written in a block form. That means this part and this part, they are actually decoupled. Okay, the ideal would be if that would be totally diagonalized. That means you have only here, here and here everything, otherwise nothing. But this is a bit I mean worse than that, but still we should be happy because at least we can decouple one mode totally from the other 2 modes. Okay, so if you now write this in this matrix form, then one can easily say that from the linear algebra that for non-trivial solution of V1, what is the necessary, I mean the required condition, that the determinant of this whole matrix must vanish. Okay, and this, when you calculate the determinant of this and will equate this to 0, that will give you the dispersion relation. So just remember this trick. That trick is actually useful for many general systems. Okay, and then the dispersion relation finally is free of V1, B1 and P1, and will simply carry relation between omega, K and other constants of the system. Okay, so what is that relation? Omega square minus K parallel square B0 square times, within the bracket you have something, so omega to the 4 minus within bracket CS square plus B0 square times K square omega square plus K square CS square K parallel square B0 square, and that is equal to 0. Okay, now we can easily understand that from this one, since we are not talking about the negative solutions of omega, so just considering positive solutions of omega, we can see that there are 3 solutions which are possible. So one is from this and 2 are from this part. Okay, so the first one is of course this one, omega A is equal to K parallel B0. So another way of writing this is omega A is nothing but omega A is equal to K dot B0. That is another way of writing. And this mode is called Alfvén mode. Okay, this mode is of super importance in different aspects of MHD, including MHD turbulence, other phenomena like heating. Okay, this type of things are there, high correlation between V and B, all things are there. Okay, now the other 2 solutions which can be obtained from this equation, okay, these 2 solution will be written in this form in a compact way. Omega plus is equal to K by root 2, and with a bigger root, square root, you can write square root CS square plus B0 square plus root over CS square plus B0 square whole square minus 4 CS square B0 square times K parallel square by K square. Okay, clear? Now for omega minus, as you can see, it will be K by root over 2, then the same thing, root over square root over all, and then you have CS square plus B0 square, then you have the distinction between these 2. So here there was plus and now you have minus. Okay, and then within the bracket you have the same factor, same term. So this one is known as the fast mode, and this one is known as the slow mode. Okay. Now it is true that when your equations are incompressible MHD equation, that means all the velocity vector is solenoidal. Okay, all the k dot v type of things, there being zero, this type of thing, I mean like divergence of v, or in Fourier mode actually k dot v Fourier is equal to 0, whatever. Okay, so in this type of case you can simply understand that Alfvén mode is an incompressible MHD mode, because at this condition only one mode survives, and that is the Alfvén mode. That you can actually check. So my suggestion will be you start from here and you just try to understand that which things should be changed, or rather you can start directly from here, which thing should be changed if you have incompressible MHD. So one thing is very simple to see, that you have this one is 0, this one, right? So this one is also 0. So this can be a bit this can be a bit tricky. So just try on your own and show, and actually you will see that this is somehow very easy to show, that only one wave mode will then retains, and that wave mode should look like this. I mean should have a dispersion relation like this. Okay. Then another point is that actually one can show that. So my request for you to show that the velocity, the phase velocity of the slow mode is actually less than or equal to the phase velocity of the Alfvén mode, and that will be less than equal to the phase velocity of the first mode. So can you do just a simple algebraic calculations and tell me? So I can help you. Okay, but before that, let us do something very interesting. First of all, I said that if your set of equations are are of incompressible nature, then I said that just you can check and verify that the only dispersion relation which you get is that of the Alfvén modes. But we can do something very easily. We can just say that for if we just take the dispersion relation of the Alfvén mode, which is omega is equal to omega A is equal to k parallel B0, and then we simply write this expression for omega in this equation, that omega square minus k parallel whole square B0 square times V1 x is equal to 0, and which simply says that as this one is 0, then this equation will be true even when V1 x is non-zero, right? Now what happens for these two equations? So for example, if you write these two equations in a set of linear equations, then you will see that this one times V1y plus this one times V1z is 0, and similarly this thing times V1y plus this thing times V1z is also equal to 0. Now so it is nothing but an eigenvalue problem, right? So in this, for this matrix, you just so try this value. So when omega is equal to, so you just check. I mean, not exactly eigenvalue problem. I am not really very much correct in that sense, but just to tell you that I am just checking how does it behave when omega is equal to k parallel B0. That's it. Then this part is 0. So this part does not need to be 0, and what will be the form of this part, that I will check. So under that condition, this part will be, so we have these two equations, I just said, that omega square minus k perpendicular square ca square minus k square B0 square times V1y, okay, minus k perpendicular k parallel ca square V1z is equal to 0. Okay, and then minus k perpendicular k parallel ca square V1y plus omega square minus k parallel square cs square v1z is equal to 0. Okay, now if I just use this value for omega, then I will simply get minus k perpendicular square cs square plus b0 square times v1y minus k perpendicular k parallel cs square v1z is equal to 0. Then here you have minus v perpendicular k perpendicular k parallel cs square v1y minus k parallel square cs square plus b0 square v1z is equal to 0. So I just eliminate v1y from both these equations, and then I will have these two things to be equal, from where you can easily cancel k parallel and k perpendiculars accordingly, and you will have this relation. So one possibility is of course v1z is 0. The other possibility is cs to the 4 will be equal to cs square plus b0 square whole square, as cs square should be positive. Then cs square should be simply equal to cs square plus b0 square in case v1z is not equal to 0, and that simply gives us b0 square is equal to 0, and which is not possible, which simply violates our main assumption that there is a magnetic field. Otherwise this is no longer an MHD fluid. So this is impossible. So v1z must be equal to 0, and similarly you can show v1y is also 0. So the only non-zero component of v is the x component, and so our v can be written in this way. But our propagation vector, as our smart choice said, is equal to 0, k perpendicular and k parallel. So we can simply write that k dot v is equal to 0. Okay. So the particle velocity is perpendicular to the wave propagation, and that's the definition of a transverse mode. Okay. So when you simply pluck at one point of a tense string and then release it, then basically the string vibrates, and you say that it vibrates and the vibration or the part, disturb is propagating like maybe in this direction, but the particle is vibrating in this direction. So this is nothing but a classical example of a transverse wave. And you all know that all this like light, heat, all these electromagnetic waves in vacuum at least, okay, so vacuum at least, they are always perfectly transverse waves. Okay, so just to tell you that so transverse simply means that the particle velocity and the propagation direction, they are mutually perpendicular. Okay, now simply once again, so as this is the case, then k dot v is also equal to 0. It simply says that v perpendicular, simply that v, okay, so in our case v is parallel to x, okay, as we saw, and so the Fourier component of v is also parallel to x. You can simply say that this is, well, here either you can use Fourier component, or you can say that the amplitude of the plane wave solution. Okay, and then this is also according to x, along the x direction, and then we can actually get k dot vk, which is the Fourier component of v, which is also 0. So it simply says this is nothing but the incompressibility condition. So this wave mode is also incompressible. Okay, and that's why even in this wave mode appears as a totally decoupled mode from the other two modes in the compressible MHD. The nature of this mode is incompressible in nature. Okay, now my question is, what about the dispersive nature of Alban wave? Well, the dispersion relation is this one, and here the question is how to define the phase velocity. So the phase velocity actually is given by parallel. So it's omega by the wave vector parallel to the direction of propagation, and that's exactly the should be the proper definition of phase velocity, and that is simply given here just by VA. Okay, on the other hand, if you do VG, and VG is nothing but this, and that will be equal to this, and if you do this one very rightly, you will see that is also equal to, so Vg equal to Va. So Vg is equal to Vp, and they are independent of K. So this is a non-dispersive mode. Okay, non-dispersive mode as Vp omega by K parallel is equal to Vg is equal to K omega. Okay, so this is what is the brief story about the Alban mode. What about the other two? So there are two other modes. One is called the fast mode. Okay, so that is this one. This one is called the fast mode, and this one is called the the slow mode. Okay, it's not first, it's fast mode. Okay, so fast mode has this dispersion relation. So omega plus is equal to, we just call it as omega plus and omega minus for slow modes. Okay, so omega plus is K by root 2, and this whole factor, as I said. Now this factor, just try to understand, this factor can have a maximum value when this term is minimum, because this is getting subtracted from this one, and this term is minimum when K parallel is equal to 0. So that means when the propagation is perpendicular to B0, right? That means the propagation vector has no parallel component, and in this condition K parallel is 0, so this is 0, and this total thing within the bracket is nothing but CS square plus B0 square. Okay, so so that is actually CS square plus B0 square whole square, and when you take the root over, that will give you simply CS square plus B0 square. Now, so this is the maximum case, and the minimum case is when this one is almost equal to K, and then what happens, you have CS square plus B0 square whole square minus 4 CS square B0 square, which is nothing but CS square minus B0 square whole square. Now we don't know which one is greater. So if your beta is greater than 1, big value, then CS is actually greater than B0. So it should be then this one should be equal to CS square minus B0 square. Okay, the whole thing under, taking into account the roots as well. And if we are considering the case of a low beta case, then this one will be simply B0 square minus CS square. Okay, so in the first case, okay, so what happens that in the first case, so just a minute, yeah, so let me just start by saying the maximum case. So for the phase speed, which is omega by K, that is equal to V, and that will simply be then given by the maximum, so this, that will have a maximum value, which should be then, so you can easily understand that omega plus by K, which is the phase speed, that will have the maximum value when this will have the maximum value. So the maximum value will simply be root over CS square plus B0 square plus CS square plus B0 square. So you will have a root 2 times root over CS square plus B0 square. Okay, and then you can simply say that this is exactly what is our phase speed. So phase speed is root over Cx square plus B0 square. This root 2, and there will be another root 2 which cancels each other. So this is the case where this value has a maximum value, this one. Okay, and this is this corresponds to the maximum phase speed. Now what will be the minimum phase speed? So minimum phase speed means for high value of beta, this is CS square minus B0 square. So when you just write this total thing, it will be CS square plus B0 square plus CS square minus B0 square. So you will have only 2 CS square. So again root 2 and root 2 will cancel each other. So you will have a CS for high beta. So for high beta, this fast mode reduces to nothing but to a acoustic mode, sound wave mode. And for low beta, the fast mode reduces to an Alphen mode. Okay, and that actually when its propagation is perpendicular to beta B0, because in that way when this is minimum, when K parallel is almost equal to the K total, so that means the propagation vector is almost aligned with respect to the B0 or aligned to the B0. Okay, but this is also the transverse mode. Okay, so you see that when at the minimum value, so minimum phase speed corresponds to the sound speed for high beta and corresponds to Alphen speed for low beta. I have made some mistake, just a minute, let me just, this one, sorry, B0. Okay, this is the Alphen speed as well. Now it is true that here we have written just a minute, so what about the nature? So yeah, it is true that I have at some point I have to write this, that is equivalent to B0 over here. Okay, and so that is B0. So yeah, okay, so B0 is the Alphen speed for us. Okay, so it is not K dot VA, but it's K dot B0. Okay, now what is the story for slow mode? So for slow modes, what happens? So omega minus is equal to K by root 2 and this times the whole factor, and the whole factor again is maximum when this one is 0 and it has CS square plus B0 square, and is minimum when this thing inside the root over is equal to, once again this is then just 1, and you have the whole thing as mod of CS square. So the whole thing root over is mod of CS square minus B0 square. So then this phase speed is actually is equal to CS when your system's beta is less than 1, and this is converted or reduced to the Alphen mode when your system has a high beta. So if your system has a high beta, the fast mode, okay, becomes acoustic, but the slow mode, okay, becomes Alphenic. When your system has a low beta, the fast mode becomes Alphenic, the slow mode becomes acoustic. Okay. Now my question to you to think, are fast and slow modes dispersive? And actually if you think very deeply, you will see that none of these three modes are dispersive in nature in general. Okay, so here actually at this point I am just putting an end to the discussion of the waves in MHD, and it is a very vast chapter. There are several books which are only written on the waves in MHD. Okay, so this is a vast subject of research and analysis. Okay, so in various, so now the question is, in the context of space and astrophysics, these wave modes are very, very important because this leads to several phenomena and this controls different type of behavior of an MHD fluid, and that's why a very good knowledge, even if not much mathematical knowledge, but at least a very good knowledge about those three modes are very much important. So one thing to be said, that unlike the incompressible Alphen mode, the last two modes, which are the fast mode and the slow mode, they are only appearing when your system is compressible, when you are talking about MHD, compressible MHD. Okay, so that's why these two modes are known as sonic modes, and they are called fast magnetosonic mode and slow magnetosonic mode. Okay, since there are the two contributions in general, one is from magnetic field, another is from the acoustic wave. Okay, that's why they are called fast and slow magnetosonic or magnetoacoustic modes. Okay, all these vocabularies are there. Okay, so from the next lecture we will start discussing two or three interesting applications of MHD, and then I will pass to the discussion of turbulence as well. Okay, thank you very much.